Hello everyone. Uh, I'm Ganesh from Kekewag Institute of Engineering Education and Research, Nashik. Welcomes in this video. In this video, we are going to see the design of FC TCR, that is design of fixed capacitor thyristor controlled reactor. So in this video, I'm going to give you one problem statement, and we will design the size of capacitor and thyristor control reactor for the this case, and we will we'll simulate that in the MATLAB in the next video. So let's see the problem statement. Design and simulate fixed capacitor thyristor control reactor, that is FCTCR scheme for following condition. The supply voltage is 230 volt, 50 hertz single phase AC supply. The line resistance is zero point 0.1 milliohm and inductance is zero point 0.1 picohenry. The load condition is given as the load is 10 kilowatt and the power factor maybe varies from unity to power factor, zero point 0.6 power factor lagging. So the power factor is varies from 0 to zero point 0.6, and for that we have to design the FCTCR scheme. So let us see the single line diagram of the FCTCR. So here you can observe this is the single phase source 230 volt 58 single phase AC supply, which is given in the problem. Then the line resistance and inductance is given 0.1 milliohm. L is zero point 0.1 picohenry. It is at the common PCC, the point of common coupling, the load is of 10 kilowatt, minimum power factor of zero point 0.6 and maximum power factor of unity is connected. On the same bus, I have to connect the FCTCR scheme such that the reactive power supplied by the source must be zero or power factor must be unity. So this is the FCTCR scheme where the capacitor is fixed and TCR is controlled through the AC voltage controller, that is anti-parallel SCR. These two are SCR. This is the thyristor T1 and this is the thyristor T2, which is connected here. So this is the FCTCR scheme. So let us design the size of capacitor and inductor. So what is the load power given? The load power is given as the 10 kilowatt, that is a 10,000 watt. For unity power factor, the reactive power requirement is a 0. Okay, so load reactive power requirement is a 0. For zero point 0.6 power factor lagging, the phase angle is cos inverse of 0.6, that is 53.13 degree. This angle is in degree. So how I can calculate the reactive power requirement of the load? So QL is equal to PL into tan phi. PL into tan phi. From this phasor diagram you can understand that is a power triangle diagram. So QL is equal to PL tan phi. So 10 into tan of 53.13, it comes to 13.333 kVAR. So you can say QL is equal to 13,333 VAR. FC should, so our fixed capacitor should be capable to supply the maximum reactive power. That is the maximum reactive power requirement of the load is 13,333 VAR, which must be supplied by the fixed capacitors. Hence, the capacitor rating should be 13,333 VAR. You can treat it as a minus 13,333 VAR because capacitance supplies the reactive power, hence it can be treated as a minus. Hence the capacitive reactance, how we'll calculate the capacitive reactance? We know that X is equal to 2 pi FC. So from this formula, first we calculate the XC. X is equal to V square upon QC. The voltage is 230 square upon QC. So it will give you 3.9676 ohm. Hence, the capacitance required C is equal to 1 upon 2 pi XC, that is 1 upon 2 pi 50 into 3.9676. So it comes to 802.27 microfarad. This is the size of capacitance required while we are doing the simulation, or you can take the reactive power in the simulation diagram. Now we will see how to decide the size of TCR, that is the inductor. So we'll decide the size of this inductor. So when the power factor is unity, suppose the power factor is unity and this capacitance is fixed connected. Hence, at this condition, the TCR should be capable to absorb the maximum reactive power. So what is the maximum reactive power which is supplied by the capacitors? Though there is no requirement of reactive power by the load at unity power factors. Then also the capacitance supplies the reactive power of 13,333 VAR, which must be absorbed by the TCR. Hence, the maximum reactive power rating of the TCR is equal to 13,333 VAR. Hence, the maximum reactance is XL is equal to V square upon QL. Again, it comes to 3.9676 ohm. Hence, the inductor size required. So, XL is equal to 2 pi FL. Hence, L is equal to XL upon 2 pi F. So, it comes to 12.6 millihenry. To ensure the power factor of the supply to be unity, the reactive power supplied by the source is 0. So choose the reactive power rating of FC TCR higher than the calculated. So calculated value is 13,333 VAR. So we'll choose the QL and QC values as 14,000 VAR. So this is about the design of the power circuit. Now let us see how to design the firing angle circuit or control circuit. Here, the reactive power supplied by the source must be 0. So we want to reduce the reactive power supplied to the 0, so that the power factor of the source must be unity. Hence, the reactive power measured from the source is compared with the 0 value. It should be compensated. It is in -1. Then it is given to the PI controller. So PI controller will calculate the required angle. So minimum cap for the equal angle is 90 degree to 180 degree. We know that in a TCR scheme, the firing angle is controlled only from 90 degree to 180 degree. So it is controlled from 90 degree to 180 degree. It will calculate the firing angle alpha. This firing angle is given to the triggering circuit, where the trigger pulse is generated G1 and G2, where G1 is the trigger pulse to the thyristor T1 and G2 is the gate pulse for the thyristor T2. So this is about the control circuit design. In the next video, I will simulate this FCTCR with the design values in a MATLAB. So watch the next video also for simulation of FCTCR. Kindly subscribe my channel and share with your friends. Thank you.